Hi, good afternoon, everyone. I'm Mukesh Raghav. I'm working with Professor Amit and Professor Ramanujan. So today I'll be addressing the questions where we left last time. For example, what are the effects of curvature, shear flow, and nonlinearity on the tropical waves? So before starting, I'll quickly summarize where we were last time. So we started with a few of the important questions that are of interest in the tropical meteorology. For example, what is the nature of convection, the relation between nature of convection and dynamics in the tropical systems? The reason we study these waves are that these waves coupled with convection uh, are attributed to a large scale variability in the tropical systems, what are called the synoptic scales. So this is one of the reasons that these waves are studied. And for example, another interesting question is this organization of convection and rainfall at a large scale in the tropical systems. So, and the yet another interesting question is there a sort of connection between these tropical and extratropical systems, and can such a connection be addressed by such waves? So these are the sort of rough motivation of why one studies these waves. So now the small aspect ratio of the atmospheric system, that is the lateral dimension of the atmospheric system, is very large compared to the z direction dimension. That allows one to study these waves with so-called very simplistic model called the shallow water equations, which is just a quasi 2D approximation of the 3D Navier-Stokes equation. And you can study it on a topography, but we'll be dealing with a flat topography in this case. So this is nothing but I think it's lost there. So it's a single layer constant density fluid where the fields are the perturbation height and the velocity fields in the x and the y direction. So these are the governing equations. There is a momentum equation, and this, remember, we are still dealing with the inviscid form of these equations. So there is no viscous term involved, and there is an equation for the perturbation of the height field. Uh, so we start with looking at if you work on the tangential plane approximation, that is, you draw a tangent plane at a certain latitude, and you study these equations with the boundary conditions that the fields are periodic in the zonal direction, so zonal direction being this one, and they're vanishing as one goes away from the particular latitude. So this work was done fairly back by Matsuno, and interestingly, you get three family of waves. So there are these eastward propagating and the westward propagating inertial gravity waves, which are fast, and there is a family of Rossby and the mixed Rossby gravity waves, which are slowly propagating westward modes. So now we ask the question that if rather than studying these fields system on a no flow base state, if you introduce a shear flow in this system, what changes or how these waves are affected? So we could see, for example, that the mixed Rossby gravity and the Rossby gravity waves, that is this family of waves, is getting most affected in presence of shear flow. And I won't go into the theoretical details, but there is a theoretical understanding as to why there is such the case and why the fast modes are not affected by shear flow. So, but interestingly, we see that if you look at the asymptotic behavior of these dispersion curves, you see that when there is no shear flow, the phase speed goes as 1 by k square. But in the presence of shear flow, it goes as some fraction of the Froude number that you associate with. So we tried this for a variety of independent sets of shear flow profiles, and we found a similar behavior, this similar asymptotic behavior of the phase speed. So and so we are interested in, is there a theoretical way to address this question, that what determines this alpha in some sense? And there were certain other observations. For example, the eigenfunction of the Rossby waves got more equatorially trapped, meaning it was more trapped towards the equator in presence of a positive Froude number rather than a negative Froude number. And for example, the short waves are stable for a largest range of the Froude number sense. So moving on, So then we started asking the question that now what happens if you relax this assumption of the planar geometry and you start working with the full set of spherical shallow water equations. Uh, so again, we took the similar path of linear, studying the system in a set of linear and nonlinear theory, and first studying it for a linearized system about a no flow base state. And the governing equation changes in certain fashion. There, the sine theta is appearing because of the fact that we are dealing with the spherical geometry and you're not linearizing this term. So interestingly, we see that there is a certain critical wave number before which, so the black curve is the spherical case and the blue curve is the planar case. So you see that there is a critical wave number before which the spherical modes are slowly propagating than the planar ones, after which the behavior changes. And this is consistent with both the inertial eastward and the westward inertial gravity waves, that there is certain critical wave number after which the spherical modes are fast propagating than the planar case. We don't have a theoretical understanding of it yet, but we are looking into it. And the behavior, the deviation is not so much for the Rossby waves. It's monotonic and not significant. So these were the findings for the linearized case about a motionless base state. And then we asked the similar question that now if we introduce a shear flow in the problem and study the similar equation on a spherical boundary, what happens? And we could see a similar behavior as we mentioned earlier. There is the asymptotics of the planar case is mimicked in the spherical case also. However, there is a larger spread and the modes are not moving as fast towards the asymptote as they are for the beta plane case. So that's one thing, and there are minute changes in terms of the slope of this function, but yeah, those are not very high. Uh, and then, so then we developed have a set of nonlinear movies for these individual modes that if you evolve them nonlinearly, how would they change, and I can play that. So the n in this represents the mode, the meridional mode number. So n equal to 1 means that there are two sort of gyres. So if this was a linear wave, it would just go, for example, westward with the phase speed, but you could see some undulations along the latitude in case of a nonlinear system. And this, there is still a periodicity there, and the period changes significantly, but it's still propagating westwards. So this is for the Rossby mode, and I have similar movies for example, other modes also. And as you can see, for example, so these gyres have a tendency to go off equator when you introduce a nonlinearity in the system. And that is one of the reasons that we study these waves, and that might lead to answering the question that can these waves propagate far enough from the equator and have some connections with the extratropical systems, and can, for example, address the question of energy transfer between the equatorial and the extratropical systems. And I have another movie for similar mode, which is, this is a fast forward. So the previous ones for the Rossby, which is a slow moving westward propagating wave. This one is for a relatively faster mode, and you could see these off equatorial gyres in this case also. So, but this is a very preliminary work, and we need some further analysis to make any comments on this. So to conclude, we can see that in the linear theory, the faster eastward and the westward inertial gravity modes are the ones which are highly affected by the effects of the curvature. So for eastward inertial gravity waves, we can see that they become, the spherical eastward inertial gravity becomes faster after a critical K, and that is also the case with westward inertial gravity. And this critical K increases with the meridional wave number. When you introduce shear in the problem, there is a larger spread in the Rossby modes compared to the planar case, and it asymptotes slower than the planar case. And as far as we could see for certain fluid numbers, the mixed Rossby gravity wave, which was present in the planar case, seems to be absent in this case. So this is, this still a work in. So one of the, for example, another questions that we want to address is if there is a significant transient growth, as we saw in the planar case also, in a spherical case, and for example, is it possible to come up with a theoretical explanation to the asymptotics of the mixed Rossby and the Rossby gravity waves, and what are the effects? How does the nonlinearity changes the unstable modes of the linear system? And then as far as data is concerned, we want to filter the satellite data to reproduce some of these dominant modes in the system. And this is the broader question that we want to introduce the effects of convection and see how the eigenfunction and the various things change with that. So that's it. Yeah. Thank you.
Thank you, Mukesh.